Welcome. In this video, we are going to talk about free energy, and we've got two objectives. One, we want to be able to predict the sign of delta G, or the change in free energy for a reaction, and we also want to be able to calculate the value of the free energy change for a reaction. And what is delta G? Well, it's the change in free energy, and it's something that has to do with whether or not a reaction is spontaneous or thermodynamically favorable. So we have seen that whether or not a reaction is spontaneous depends on the values of the change in enthalpy, that's our delta H value, and the change in entropy, which is our delta S value. And delta G is known as the Gibbs free energy, and you can see the equation for it right over here. And it is a value that combines the impacts of enthalpy and entropy and kind of puts it all together into one value. And the significance of delta G is if delta G is a negative, then we say the reaction is thermodynamically favorable. And what that means is that is a process that will just spontaneously occur in nature. If delta G is positive, the reaction will not be spontaneous. So it won't just happen on its own spontaneously in nature. So delta G is a really key value, and it tells us whether or not a reaction will occur. And it's combining together these two energy variables, the change in enthalpy and the change in entropy. And what we want to be able to do, we want to be able to calculate delta G given delta S, delta H, and T values. So here's this equation bringing it all together. So delta G equals delta H minus T delta S. At the end of this video, we'll talk through an example of how to use this one. Another equation that you want to be able to use is you can calculate delta G given a table of standard heat, I almost said heat of formation, but it's the Gibbs free energy of formation. But this equation looks really similar to that heat of formation equation that we've seen. So this is another equation you can use. If you're given the Gibbs free energy of formation of the reactions and products, you can use this one. And then we want to be able to interpret signs. So predict the sign of delta G in a given scenario and evaluate the impact of delta H and delta S values, what impact they will have on the sign of delta G, and therefore the favorability of the reaction. So we're going to start out by focusing on sign. So one thing that we should be aware of is that delta G tells us whether a reaction is spontaneous or not. And some processes can be spontaneous at one temperature and not another. One example is the freezing of water. So if you have a glass of liquid water sitting at your desk and it's at room temperature, it is not going to spontaneously freeze. But if you stick it in your freezer that has a temperature of -4 degrees Celsius, then it will spontaneously freeze. So this process right here is spontaneous at low temperatures, so like in your freezers, but it is not spontaneous at high temperatures. So that's something to keep in mind, and we're going to think about why that is in a moment. But first, let's just kind of evaluate what's going on here. So let's look at what's the sign of delta S for this reaction. Well, we're going from a liquid to a solid. So we're turning this into a more ordered state. So there's going to be a decrease in the disorder. So there's a decrease in entropy for this reaction. And then if you think about the sign of delta H, if you stick some, room temperature water, here's my picture right here. Imagine you stick a beaker of room temperature water in your freezer, and it's going to turn into ice. The heat is going to transfer from the high temperature object to the low temperature object. So heat is going to leave the water. So this process of freezing is exothermic. So it's got a negative delta H. And if we think about the sign of delta G, well, how do we predict that? Well, keep in mind that the sign of delta G is related to whether or not it happens spontaneously. So at 25 degrees Fahrenheit, that's -4 Celsius, this process is spontaneous. So that means that at this temperature, delta G is negative. At this higher temperature, it is not spontaneous. So this higher temperature, delta G is positive. And that's because the delta G is delta H minus T delta S. So at different temperatures, you might end up with a delta G that is negative or positive based on what the temperature is. Let's look at some more examples here. So here's some examples of different processes. These top 4 examples, these are processes that are always spontaneous. Remember, if it's spontaneous, that means the delta G is negative. So what we might notice that these top 4 have in common is they have a delta H that is either negative or 0, essentially, and they all have an increase in entropy. So we say that these 2 variables are favorable. So looks like it's thermodynamically favorable to have a decrease in enthalpy and an increase in entropy. So if your reaction checks both of these boxes, if it's exothermic and the entropy increases, then it's going to be thermodynamically favorable. It's going to be spontaneous. It will happen on its own in nature. Okay. If we look at these examples, you see how these say these are not spontaneous. So, and what they have in common is both of these processes are endothermic and entropy decreases. So if these 2 things are true, these are not favorable. So no matter what the conditions are, these processes are never going to happen spontaneously. Okay, then these examples down here show that, well, if the other scenario would be is what if the signs are actually the same, right? So like what if you are exothermic, so like what if your delta H is negative, but your entropy change is negative, then you're going to be favorable sometimes, only at certain temperatures. If you are endothermic and your entropy is favorable, so if both these values are positive, it's the same thing. You're going to be favorable at some temperatures, but not others. So summary of your favorability here is when you're thinking about, let's think about the entropy variable here in this equation. So remember, I'm going to rewrite this equation here. Delta G equals delta H minus T delta S. When your delta S is favorable, so if you have a positive change in entropy, if your entropy increases, the reaction is going to be more favorable at high temperatures. Because if you look at what the temperature variable here, the temperature is being multiplied by your delta S. So if you're the temperature is going to like magnify the impact of the entropy change. So if your entropy change is favorable, so if this delta S value is favorable, then at a higher temperature, that process is going to be even more favorable. If your delta S is not favorable, so if you have a decrease in entropy, then the opposite is true. These would be more favorable at low temperatures because you want to minimize the impact of that entropy change. So with delta S is positive, it's more likely to occur at high temperatures. If delta S is negative, it's more likely to occur at low temperatures. If both variables are favorable, it will occur at all temperatures, so it's always going to be favorable. And so remember what we mean by favorable is we mean like if your delta H is negative and your entropy increases, that's what we mean by favorable. And then if neither one is favorable, so if it's endothermic and the entropy decreases, that type of reaction is never going to be favorable. So notice if we go back to our freezing example, this one had a favorable delta H. It's an exothermic process, but the entropy was unfavorable. And so this was a process that is spontaneous at lower temperatures, but not at higher temperatures. So the water will freeze in your freezer, but not at room temperature. It's spontaneous at cold temperatures and not warm temperatures. So that's an example of that, kind of that in action here. Here's another way of kind of summarizing the various possible mixes of sine and what impact that has on G. So if you just think about it, mathematically, using this equation right here, delta H minus T delta S, if H is negative and S is positive, A negative minus a positive will always give you a negative number no matter what. And then the opposite is true. A positive minus a negative will always give you a positive value. So this top scenario is always favorable. This bottom scenario is never favorable. And then here in the middle, this is where it gets more complicated. If you have a negative minus a negative or a positive minus a positive, these can be positive or negative depending upon the magnitudes of these values here, right? So how big is this number compared to this number right here? So these are going to be temperature dependent because the value of the temperature is going to impact the value, the second number right here. So the larger the temperature, the larger the second value is going to be. Here's another table. Some people have different ways of kind of summarizing these relationships. So this is a summary using the kind of greater than, less than sign. So this is favored at all t, no t, high t, low t. So this one's organized a slightly different way of the previous table. So this is something else you might find helpful. If you like it, you can pause it and, take a look at this one. Let's try another practice problem here, predicting the sign and predicting whether it's more likely to occur at low temperature or high temperature conditions. So why don't you pause the video and try these two sample problems if you haven't tried them already. Okay, and then I'm going to go over the answers. I'm going to trust that you've stopped and tried this. Okay, so this first one, we are looking at the process of dissolving salt in water. So I'm turning solid salt into aqueous salt. And I want to know the sign of delta G, delta H, and delta S here. So with delta G, when you're trying to figure out the sign of delta G, you should just ask yourself, did it happen? So if the process occurred spontaneously, then the delta G must have been negative, period. Because anything that's thermodynamically favorable, that's spontaneous, has a negative delta G value. All right, let's look at delta H. It made the surrounding temperature decrease. This sounds like an endothermic process. So the delta H is positive. That's not favorable. But then let's look at the delta S. It goes from a solid to aqueous, so it's becoming more disordered. So the delta S is positive. So it's got a favorable change in entropy. And then if we think about, is this more likely to occur at high temperatures or low temperatures? Well, both of these values are positive numbers, okay? And in order to end up with a negative delta G, we would want this number to be large, right? So the larger the second number, the more negative the delta G is likely to be. So this process is going to be more favorable at high temps. And if you're having a hard time kind of seeing how that works out mathematically, what you can do is you can pick a couple of numbers here. So what I like doing is I like picking this first number as being like 10. So let's say this number is 10, right? And then let's pick an extremely low number. So actually the lowest the number could be is 0. The lowest temperature, this temperature is in Kelvin, so the lowest it could be is 0. So let's say at extremely low temperature, 0 Kelvin, then your delta G would be positive 10. So that would be unfavorable at the extreme low temperature. Well, now let's pick like a high temperature. Let's say the temperature is a really big number. Let's say it's, 1,000. Okay. Then notice how in this case, your delta G is actually going to be very, very negative. It's going to be like, negative, 990. Okay. So notice how, so plugging in these numbers can help us see the impact of temperature. So the higher the temperature, the more negative the delta G is going to be. So this is going to be more favorable at high temperatures. Here's another example. We've got magnesium, which is a solid, reacting with oxygen gas. It's going to form magnesium oxide. I should balance this equation. Here we go. So notice how we're going from 3 reactant particles to only 2 product particles. Also, we have a gas in the reactant and not in the product. So those two things tell me that there's going to be a decrease in entropy. the reaction releases heat and light, so it sounds like it's exothermic. So there's going to be, whoops, I wrote the wrong thing. Exothermic, there's going to be a decrease in enthalpy, negative delta H. And the reaction happens, so it occurs. So therefore, the delta G must be negative at this under these conditions. And then we want to think about, well, is this going to be more favorable at high temperatures or low temperatures? Again, let's look at our scenario. Delta G is delta H minus T delta S. And in this case, these are both negative numbers. And when these are both negative numbers, when the change in entropy is not favorable, then the reaction is more likely at low temps. And again, if we're kind of not seeing why that is mathematically, let's try plugging in some numbers. So let's say that this is negative 10. And then this is, we'll go the extreme here, it's 0. Okay, so when the temperature is very low, the delta G is going to be negative. So it's going to be spontaneous when the temperature is pretty low. But if the temperature is pretty high, like let's say it's negative, let's say it's 100, okay? And it's going to be a negative number because delta S is negative. So you're going to have negative 10 minus negative 100, which is negative 10 plus 100, because a negative times a negative is a positive. So notice how my delta G on this conditions is actually positive. So under high temperatures, it is not spontaneous. So again, this is kind of a way to kind of mathematically work this out. Is this scenario more likely under high temperatures or low temperatures? We can see in this case, it's more likely at low temperatures. So that's what this table is kind of trying to summarize here. And you do have the option of just trying to like memorize these scenarios, but I really encourage you to try and reason it out and think about the what's going on here, the mathematics behind it. So yeah, that you understand what's happening here. And I know this is getting kind of long, but I want to do one calculation here. Okay, so let's do a calculation. And how can we use this delta G equation to actually calculate the value of delta G? So delta G equals delta H minus T delta S. And I'd say the big thing is to pay attention to units. So pay attention to units here. So when you are plugging in your numbers here, delta G equals delta H is negative 220 kilojoules, okay? And then we are going to, T is temperature. So for now, let's put down 32 degrees, okay? And then delta S is negative 780 joules per Kelvin. So hopefully right now you're noticing a couple things. You're saying, wait, this is in Kelvin. So right now these units don't match. This is in Celsius. So we need to convert this to Kelvin. So we're going to add 273 so that this is now in Kelvin instead of Celsius. Okay, so pay attention to your units here. I'll just rewrite this. So 32 plus 273, that's Kelvin. And then notice how this number is in joules, but this number over here is in kilojoules. So I need to convert my joules to kilojoules. And this is one of those metric prefixes we need to know that a kilo is 1,000. So 1 kilojoule is 1,000 joules. So negative 780 joules, it's negative 0.780 kilojoules. So I have to take my S value, I'm going to divide it by 1,000 to convert that into kilojoules. So those are really the key things to look out for. Make sure your temperature is in the right units. It needs to be in Kelvin. Make sure your units of your delta S and your delta H match up here. And then if we stop and we solve for this, we should end up getting positive 17. So try this on your own. See if you're getting the same numbers here. This works out to be over here. This is a 305 Kelvin times, 0.780 kilojoules per Kelvin, just so you know. And then negative times a negative, this ends up being a positive number. So in this case, ends up that the positive value over here is bigger than this negative value we start with. So overall, delta G is positive. So is this reaction spontaneous at this temperature? No. And the reason why, how we know that, is because it's got a positive value of delta G. Well, let's try changing the temperature. What if we try this at a lower temperature, let's say negative 50 degrees Celsius? So the temperature would be negative 50 plus 273. So the Kelvin temperature is now 223. So that's a lot smaller temperature here. So if we go and we find the delta G, it's negative 220 kilojoules minus 223 Kelvin times negative 0.780 kilojoules per Kelvin. And if you stop and solve here, you get the answer of negative 46 kilojoules. So we'll see that at negative 50, the reaction is spontaneous now. And the reason why we know is because it's got a negative delta G value. So here's an example of a reaction that is spontaneous at low temperatures, but not spontaneous at high temperatures. And we can calculate that delta G to figure out the spontaneity. And yeah, so those things we want to be able to do. We want to be able to predict the sign of delta G and think about how it's related to the signs of, delta H and delta S. We also want to be able to use this equation right here to actually calculate the value of delta G. And once we calculate the value of delta G, we can figure out if the reaction is spontaneous based on the sign of G. So if G is negative, then it's spontaneous. If delta G is positive, then it's not spontaneous. All right, thanks for watching.